All right. So the last thing we have to do before getting into exponential functions is look at these inverse trig identities. I won't prove them because this is a calculus course, not a trig course.
Yeah.
But these are just some useful identities to have if you ever need to do any substitutions. So if you want to either take a picture or write them down, you can do that.
I'll take a quick picture.
Yeah, because I don't think we'll have to use them.
Cool.
I don't think we'll have to use them at all, but the textbook includes them, so I don't want to like deprive you from textbook knowledge.
Yeah, no, okay, cool. I can grab a picture. I think that's fine.
Yeah, that's perfectly fine. All right. The derivative of exponential functions. Let's see what happens when we try and calculate the derivative of a general exponential function. And we're going to return all the way back to our limit definition of a derivative. All right. So if we want to calculate the derivative of a to the x, where a is just some number, any base, all right,
Yep.
we could calculate it using our limit definition of a derivative. So we take the limit as h approaches 0 of a to the x plus h minus a to the x over h. This is the limit definition of a derivative. You agree with that?
Yeah.
Cool. All right. And remember, exponent rules tell us that if we have a to the x plus h, that's equal to a to the x times a to the h. Right?
Yep.
Cool. So I could rewrite this limit as the limit as h approaches 0 of a to the x times a to the h minus a to the x over h. Next, in the numerator, you'll notice I have an a to the x here and an a to the x here. So I can do some factoring. Would you agree that this is a valid factoring thing to do?
I would.
All right. And additionally, I could rewrite this fraction as just a to the x times a to the h minus 1 over h. Would you agree?
Yes.
I'm just taking this a to the x in the top and bringing it down. Because if I multiply these two things together, I get the same thing as up here.
Yeah. Okay.
All right, cool. So then our derivative is going to be the limit as h approaches 0 of a to the x times a to the h minus 1 over h, right?
0. Yes.
Cool. And we can use our limit rules to split this up, right? The limit of a product of two things is the limit as h approaches 0 of a to the x times the limit as h approaches 0 of a to the h minus 1 over h, right?
Okay.
We just use our product limit rule.
Sure.
And do you remember how that works? If not,
yeah, I do.
Okay, cool. So you're valid with what we're doing up until this point.
I am.
All right. The limit as h approaches 0 of a to the x, there's no h here, right? So would you agree that no matter what value h is approaching, this is still going to be a to the x? Because this value doesn't care about what h is.
Yes.
So we could rewrite this as a to the x times the limit as h approaches 0 of a to the h minus 1 over h.
Okay.
So it's equal to the original function times whatever this limit is.
Huh. Interesting. Okay.
Yeah. So the cool thing is, if we could find some number a, right, where this limit, equals 1, then the derivative of our function would be the function itself.
Yeah.
All right? So what mathematicians did is they found the number. They found the number that would make this limit equal to 1.
I have a guess.
What is it?
Is it e?
How did you know?
Is it roughly 2.781?
I don't think I've ever told you that. I think I'm really impressed that you know that. I've never talked about e before in my life.
I learned this in 2nd grade.
Yeah.
We did a short little calculus spree.
Yeah, calculus, I don't know. They should be teaching like first graders it. Yeah. But yeah, they found the number calculus just did some math to find whatever number would make this equal to 1. And they found that number was like 2.718, whatever. It's an irrational number. It goes on forever. And we named that number e. All right?
Know what why it's e?
Okay, so we'll let you be. I'll tell you a funny story. We'll let you be the judge of this. All right. So according to according to like records, we named this number E. The person who found it named this number E just because it was some letter. They just wanted to, like, similarly to how we called like 3.14159 like pi.
Yeah.
We just named this this number E. We just picked a letter and named it that. All right. But the person who found the number, I believe, was called Leonard Euler, who is a very famous mathematician.
Yeah.
And the number is now
EULER,
yeah,
right?
And the number is called Euler's number.
Yep.
So I'll let you be the judge of whether he was being a narcissistic
there it is.
narcissistic guy, or he just chose some letter.
Just chose a random letter. Maybe.
Yeah, I don't know. I mean, I first of all, Euler is an amazing mathematician. It's really cool to see the stuff he's done. We're gonna go back to some of the cool things he's done later.
Isn't there Euler something in chemistry?
Euler, I took AP Chem. I should know. I don't know.
I don't know though. Yeah,
All right.
It sounds familiar. I could just be thinking of.
You want to know? So
for math.
A little preview of the things we're gonna do with E later. In the end of this course, we're gonna show how E is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 fact. You know what factorials are?
Yep.
Okay. It's on and on and on to infinity. That E is equal to that.
Yeah.
We're also going to show, this is probably my favorite equation in math. All right?
Okay.
And I want you to see how beautiful it is. E to the power of I, the imaginary number, times pi plus 1 equals 0.
Wow.
All of the famous mathematical numbers, E, I, pi, 1, and 0. These are all like probably the most important numbers in math.
That's like pretty crazy.
Related by one equation. So we're going to talk about why this is true, because right now you're probably like, how the hell would we raise a number to an imaginary power, right?
Yeah, what?
It's weird. So we're going to talk about this when we get into Unit 9 on infinite series, and we're going to show why this. We're going to show why. What we're going to do is we're going to show why e to the ix equals cosine of x plus I sine of x. And you'll notice if x is pi, we're going to get cosine of pi, which is -1, and I times the sine of pi, which is I times 0, which is 0. So then this will be -1 plus 1 equals 0. So we're going to you're going to understand why this is true by the end of this course. And it's probably the most beautiful equation in math.
Okay, deal.
Yeah, so a little fun stuff with that. All right,
cool.
So backtrack. We found the number that would make this limit equal to 1. And it's e. All right, so then e to the x is its own derivative. And that's why it's a really important function in physics and in everyday language, because of this property that it has. So that's the first thing we say. E to the x is the derivative of e to the x is itself. That's the first exponential rule. Now, what if we wanted to find the derivative of a to the x, just any number a to the x, like 2 to the x, blah, 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 stuff like that. Using exponent rules, here, the textbook uses an exponent rule, and I need to quickly refer to it. Okay. All right. So using exponent rules, we have a to the x here, right? Do you remember if we said, like, we took if we take a to the log base a of x, it equals x, because a and the logarithm, they're inverses, so they undo each other, right? So would you agree that e to the ln a to the x equals a to the x? And the natural logarithm is log base e, by the way.
Yes.
So we just say ln. We'll get into why that's important as well. It's just because if e to the x is such an important exponential, then log base e is its inverse, so it's also really important. So we give it a special name. All right. So there's a log rule, right? If you have the log of something to a power, right? This equals x times log base a, or no, I should have written this as something else. Let's say this is b, all right? If we have log base a of b to the x, then we can bring the exponent to the front.
Yep.
All right, that's just a log rule.
Yeah.
So I could rewrite this as, I could rewrite a to the x as e to the x ln a.
Okay.
And obviously, if a is just going to be some number, like 2 to the x or whatever, all right? So ln a is just going to be some number as well. Cool?
Yeah.
So hopefully you can see, and I'll clear my slide here. That e to the x ln a is just taking the function x ln a and sticking it inside e to the x.
Yep.
So what kind of rules do you think we'll have to use here to find the derivative? What rule do we use when we stick a function inside another function?
Chain rule.
Exactly. So let's do the chain rule. All right. So the chain rule tells us here f of x is e to the x, and g of x is x ln a.
Yep.
Because f of g of x, you can clearly see, is e to the x ln a.
Yes.
Okay, cool. So the chain rule tells us that it's going to be f prime of g of x, and the derivative of e to the x is also e to the x. So it's going to be e to the x ln a, all right, times the derivative of the inner function, right? That's what the chain rule tells us. What's the derivative of x times some number? Like if we had 2x or 3x, the derivative would be 2 and 3, right?
Yeah.
So if we multiply x... Yep. Cool. And remember, we said e to the x ln a is equal to a to the x, right? Remember on our previous slide, we said that e to the x ln a is equal to a to the x?
Yeah, I think so.
Okay, cool. And that's just because we could rewrite this as e to the ln a to the x, right? Because the log rule says that if we bring this down...
Yeah.
Right?
Okay, yeah.
And then they undo each other and we get a to the x. So e to the x ln a is the same thing as a to the x. Okay, so we can rewrite this as a to the x times ln a. And that's the derivative of a to the x.
Yeah.
So for example, the derivative of 2 to the x would be 2 to the x times the natural logarithm of 2, which is just going to be some number.
Cool.
Does that make sense? Yeah,
so that's just like the universal like function for it?
Yeah, so like a to the x, regardless of what your a value is the derivative is a to the x times the logarithm of a, natural logarithm of a. And also we could kind of backtrack and say, well, if a is e, we're gonna get ln e, right?
Yeah.
Log base e of e is 1.
Yeah.
So do you see how when that happens we get e to the x?
Yes.
So we can see that our ideas, they agree with each other.
Uh-huh.
All right. So what I need you to find with here is the derivative of e to the x being itself, and the derivative of any exponential function being if that function times the natural logarithm of its base.
Okay. Yes.
Okay, cool. All right. So that's exponentials. All right. So we did this. We did the derivatives of general exponential functions. Okay. Now let's find the derivative of the natural logarithm. All right. Because then we can use that to do the same thing where we can find the derivative of any logarithm using some log properties. Right. So would you agree we could write y equals ln x? We could rewrite this we could rewrite this as e to the y equals x.
Yes.
All right. So what do you think I'm going to do here? What kind of differentiation tactic do you think I'm going to do? We did this with the arc sign. I'm going to use implicit, right?
Okay, yeah.
All right. So I'm going to take the derivative with respect to x of both sides.
Yep.
All right. The right side is just going to be 1. And for this, we have to use the chain rule, right? Yet again, the derivative...
Yeah, because the y is in there?
Yep. The derivative of e to the y with respect to x equals the derivative of e to the y with respect to y times the derivative of y with respect to x, right?
Okay, yes.
The derivative of e to the y with respect to y is e to the y.
Yeah.
Because they're the same variables, right? The derivative of e to the x with respect to x is e to the x. If they're the same variables, right? We don't like it doesn't matter what variable we're using, right? Like we could use t, we could use d, right? The name of the variable doesn't matter. And it's the same for when we use y. As long as they're the same, they agree with each other, we're gonna get the same rule. It doesn't like the kind of variable we use doesn't matter. All right, so we get e to the y times dy over dx. All right, equals 1. Divide both sides by e to the y, dy over dx equals 1 over e to the y. But what does e to the y equal?
E to the y equals x?
Yep.
Nice.
All right, so then what is the derivative? Just with x's, without any y's. We replace e to the y with something else.
With x, so it's x times...
Right, so...
Oh, it's 1 over x?
Yeah.
Okay.
Because remember we said that e to the y times dy over dx is 1. Divide both sides by e to the y. dy over dx is 1 over e to the y. E to the y equals x, so the derivative is 1 over x.
Okay. Yeah, I follow that.
Cool. So, you can write this in your notes. The derivative of the natural logarithm of x is 1 over x. We good with that?
Yeah.
All right, cool. All right. So, before we find the derivative of any logarithm, log base a of x, all right, we need to remember a log property, all right? There's a log property called the change of base property, where you could rewrite this as log base of some other number times of x divided by log base of some other number times a. This is just a log rule.
Yeah, I think I knew that.
Okay. So we fine if we use that? If you want me to derive it, I can do that too.
Okay, I think I'm good with it.
Okay, cool. So because we found the derivative of ln x, don't you think it'd be a good idea to probably make our log base e so we can use the natural logarithm?
Yeah.
Cool. So let's write log. So if we said y equals log base a of x, we could rewrite this as ln x over ln a using the change of base rule.
Okay.
All right. So wouldn't you agree that then we could say y equals 1 over ln a times ln x? Right?
Yes. Yep.
Same thing. 1 over ln a is just going to be a number, right?
Yeah.
So our derivative rules tells us if we want to find the derivative of this, we just take the derivative of this and multiply it by whatever number we have here, right?
Yeah.
The constant multiple rule. So then the derivative is 1 over ln a times 1 over x. Would you agree?
Yeah, wait, I'm a little bit confused, I think.
That it's okay. It's just we just applied the constant multiple rule. If we have y equals k f of x, and we want to find its derivative, we take k times the derivative of f of x.
Okay.
You can also think of it. You can also think of it as the product rule, right? Right. This is it's this times this. So we're gonna get this number times the derivative of this, plus the derivative of this times this. But the derivative of a constant is 0, right?
Okay.
So the only thing the product rule leaves us with is this times the derivative of this.
Okay.
So when we find the derivative of 1 over ln a times ln x, we take 1 over ln a times the derivative of ln x.
Okay.
Got it?
Yep.
If we multiply these two things together, right, we get 1 over x times ln a.
Mm-hmm.
Would you agree?
I would.
Cool.
Yep.
So then that's the derivative.
Okay, cool.
Now, I hope now you can start to see how the natural logarithm becomes important because it's appearing in all these rules, right?
Yeah.
So just the properties of the natural logarithm and e to the x are super useful in math. They're super useful because they make these problems easier. Okay, we good with that?
I am good with that. Yeah.
Okay, let me know when you're ready to move on.
I think I'm all set. Yeah.
Cool. All right, so we did the derivative of the natural logarithm. We did the derivative of log base a of x, and now we have to do the power rule in its full power. Pun definitely intended.
Oh boy. Okay.
All right. This is the okay. I want to put this in perspective because I have to. There's conditions I have to make sure I look at as well for this one. So I put a note.
Okay.
Okay. So I want us to put this in perspective. Once we've learned the power rule in its full power, we will know how to calculate the derivative of any function.
Damn.
I could give you any function and you know how to calculate its derivative. Hypothetically, it would be hard. We'd have to do practice with it. But hypothetically, you have the tools in your tool set to solve it.
Yep.
So I want you to embrace that. Remember, like a week ago, you didn't know what a derivative was.
I didn't know what one was, and then suddenly I could find the derivative of x to the 2x. X squared.
Yep. And we went from learning one to learning every function, which is
that's crazy. I must have a good ass teacher.
He must be kind of cute too. I heard you.
He must be the most handsome man on earth.
Oh yeah. I'm so my humor is very immature. But yeah, once we learn this, we'll have the power rule in its full power, and we'll be a-okay.
Okay.
And I'm gonna show you how. All right.
And then can we do a good amount of practice, like?
Yeah. Why don't we take tomorrow at least the first part to do practice of derivatives?
Deal. I like that.
And I'll prepare a lesson for the beginning of Unit 4, but if we end up not getting to it, I'm 100% fine with that. The fact that if you guys want to extend the course another week or so, like that's all, I'm fine with that. So
okay, cool.
No time rush anymore.
Cool.
So I don't care how long we spend doing practice tomorrow.
Sounds good.
If you're curious, we could walk through that. We could walk through that really hard one if you really want to see it, but we could also just do simpler ones at the beginning as well.
I say we do a couple simpler ones, and then
maybe as a challenge at the end, we'll do a monster one to show you that you really can calculate the derivative of anything.
I like it.
Okay. Awesome. So x to the n, y equals x to the n. All right.
Yep.
We could rewrite x to the n as e to the ln x to the n. Right?
Yes.
They're the same thing.
Okay.
I could, and you agree with that because the e and the natural logarithm are inverses, so we're just left with x to the n.
Yeah.
All right. So the log rule tells us we can bring the n to the front, right? So we get y equals e to the n ln x. Cool.
E to the n ln x. Yep, that makes sense.
Okay, and notice how we haven't placed any restrictions on n. We have not placed any restrictions.
Yep.
N can be whatever it wants.
Yeah.
So if we find the derivative, then we haven't placed any restrictions on n, so n can be whatever power we want.
Okay.
All right, so let's do the derivative. It's just going to be the chain rule, right? We're taking e, and we're sticking this function inside e to the x.
Yep, okay.
All right, so
here, I just want to...
Yeah, so I'll write it up here. F of x is e to the x, and g of x is n times ln x.
F of x equals e to the x. G of x equals n ln to the x. Yeah.
So you can see how f of g of x is e times e to the n ln x.
Yes.
Okay, cool. And the chain rule tells us how to find the derivatives of these kind of functions, so that's exactly what we're going to do. We take the derivative of, so f prime of g of x is e to the n ln x, right? Because the derivative of e to the x is e to the x, so the derivative of the derivative with respect to g of x is e to the g of x.
E to the n ln x.
Yep. Then we have to multiply by the derivative of this function, right? which
Yeah.
it's just a number n times ln x.
Yeah.
So it's going to be n times the derivative of ln x, which is 1 over x.
Okay. So would it be like, would you write n over x?
Yeah.
Or does it like not really matter?
It doesn't really matter, but
Okay,
I'm just writing it like this for now.
Sure.
All right. I'll go to another slide and wrote what we've written. So the derivative
e to the n ln x times n times 1 over x.
All right. So we're at this, right? The derivative is this. We just have to simplify it.
Yes.
All right. So remember how we said e to the n ln x is the same thing as x to the n? Because we rewrote x to the n as this. So they're the same. So we could also replace this again with just x to the n.
Okay.
All right.
X to the n times n. Yeah.
Cool. All right. So let's rearrange these, because when we have things multiplied together, it doesn't matter what order we multiply them in, right?
Mm-hmm.
So we can do n times x to the n over x to the 1. Do you agree? I put the n in the front, n times x to the n over x, because as x to the n times 1 over x is x to the n over x.
Yep.
And I also just put the 1 here. You'll see why it's important, because it's x to the first power.
Mm-hmm.
And remember, we have x to the n and x to the 1 here. We know a rule for dividing exponents where their bases are the same, right?
Yeah, can we just simplify that to just x to the n?
X to the n over x to the 1?
Yeah.
We can simplify that to something, but be careful. What's the rule for dividing exponents like this?
I thought it was the exponents like over each other, but it's not that.
You're close. It's the exponents minus each other.
Okay, gotcha.
Do you remember that rule?
I do remember that rule.
Okay.
Yeah.
So I could rewrite this as n times x to the n minus 1.
Okay. Which is
Ta-da!
Which is our original one.
Yeah. So that's the power rule, and it works for any number.
Got him.
So so now we've shown that the power rule we know and love applies for any number.